So we already learned about the convolution neural network. So this is the general architecture that we learned before. So now I'm going to teach you the basic concept of recurrent neural network. What is recurrent neural network? Recurrent neural networks, we also know as RNN. So usually this is a class of neural networks that allow the previous output to be used as inputs while having hidden states. So the keyword is this one, previous output. So the advantages, we can see that there is a possibility of processing input of any length. Any length means if your data has some length, it doesn't matter about the length. Maybe the length is 5 or the length is 10, the length is 20, it doesn't matter with the length. And model size not increasing with the size input. So this is the advantage. The computation takes into account historical information. So when we have some data, like the data in the T1, let's say T1 is the January, T2, let's say this is the February, T3, maybe this is March, and so on. Until, let's say, I have the data until T11, until November. So I can take into account all the historical data with this neural network. And then weights are shared across time. So every of the data which have weight, let's say the data in the T1 has weight, and the data in the T2 has also weight, and so on. So the weight can be shared across time. But the drawbacks, the computation is slow. And it has difficulty of accessing information from a long time ago. So for example, if we have like T1 until T11, it is still okay. But if we have like T1 until T1000, okay, so if it is too long, it doesn't work. And cannot consider any future input for the current state. Of course, we cannot have the input of the T1001 to improve it. So this neural network, the RNN, is typical with some application. If you look at the basic or the traditional neural network, this traditional neural network means that we have the X, and then we will input into a layer, hidden layer, and then we will predict. So there might be some coefficient or some bias. Because this is one-to-one, because we have one variable for the input and we will have one variable as the target. But we can have one to many. For example, if we want to have music generation. So music generation means if we want to generate a kind of music, let's say I have an input. I want to input a music, a jazz music. Okay. If I want to input, if I have to input jazz music, then I can have some outputs. Maybe jazz type 1, or maybe jazz type 2, jazz type 3. Or something like the melody in the batch number 1, in the melody in the batch number 2, the melody in the batch number 3. Okay. There's another kind of application, we call it the sentiment classification. The sentiment classification means if we have some words, we want to know whether it is a positive or negative. For example, if you go to the online shopping, okay, I really love to buy this laptop. Okay, so this kind of review will appear in the online shopping, and we can say that okay, this is a positive review. So in the sentiment, usually we have positive or negative. Let's say I have another words. This product is really bad. Then because I know that this is toward negative, then I can make this classification, or I can make this class as negative. So this is what that mean by the sentiment classification. The input can be many. Okay. The input is the what this product is really bad. Okay, I know that those words is the word negative because we have the word bad. Or we can have another input. I really love to buy this laptop. Okay. So there are many inputs of this one, and because of this word love, then I can put it as the positive. So the result is only one, either positive or negative. There's another kind of application, we call it name entity recognition. Okay. So in the name entity recognition, we call it many to many. There are many inputs and there can be many outputs. So for example, name entity recognition. This is one of the important classification with the RNN. Let's say this one. So I have an article. So this is an article, and then because it is a text until this part, okay, the library can recognize that this is an organization. Okay, ORG. ORG means organization. And then by FBI agent, yeah, maybe because this is a text, so they cannot recognize this FBI. This one, okay, this is a person who criticized Trump. Okay, this is a person. And then, yeah, because this one is a text, like this one, it cannot recognize it. FBI, okay, this is the government entity. Okay, GPE is the government public entity. And okay, we have Trump, which is this is person, and then okay, this is person, okay, this is organization, and so on. So it means for every of these texts, if it is the input, then we will check whether it is organization or it is a person or it is a government public entity. So yeah, we can have this input, many input with many output. We can also do with the machine translation using the RNN. Machine translation means we can translate. So for example, yeah, if we have the English, I will go to school tomorrow. So what is the result in Korean? So maybe the word is 학교 내일 학교 가겠습니다. So It means when we have the word I will go to school tomorrow. So there will be many input, but the output will not be the same or will not give you a similar sequence. So there will be another many output. It depends on the machine. It depends on the words. It depends on the structure, or it depends on the grammar. So we call this is the machine translation. There are some variants with the recurrent neural network. We call it the GRU or LSTM. Maybe it is not that familiar for you, but this just gives you some introduction about this RNN. GRU means gated recurrent unit. And the LSTM, it is long short-term memory units. So the GRU and the LSTM, it can deal with the vanishing gradient problem encountered by the traditional RNN. The last time I mentioned to you about the vanishing gradient problem, the problems in the neural network. So the traditional RNN also have the vanishing gradient problem. And the GRU and LSTM can solve, or it can deal with this vanishing gradient problem. So the LSTM is the generalization of GRU. This is the architecture of the GRU, and this is the architecture of the LSTM. So let's focus on this one. And let's focus on this one. Maybe I didn't, let me jump a little bit. So the notation, we have update gate, we have relevance gate, we have forget gate, and we have the output gate. So what is update gate? It is how much past should matter now. It will be used in the GRU and LSTM. Relevance gate. So it will drop the previous information. It is also used in the GRU and LSTM. But the two, forget gate and output gate, the forget gate means it will erase the cell or not. And the output gate, how much to reveal of a cell. So it is only in the LSTM. Okay. So you can look at this symbol U, R, F, and O. So if I look back to this architecture, U, it means the update gate. We will update any information input to this architecture. We will update any information entering into this layer. And then we have the relevance. So we want to check the relevance of the information from the hidden layer. What is the relevant information, and it will be used for the next stage. In the LSTM, it includes update and relevance, and it also includes the forget and output. It means if there are some information which is not important, let's forget it. After we forget the previous information, we will update. After we update it, then we will find what is the relevance to this architecture, and it will be combined into one output for the next input. So if you know for every layer, there might be some mechanism with this gate. Whenever we have the vanishing gradient problem, okay, this is one example. One example of unstable behavior that you may encounter when training a deep neural network. If the neural network has many hidden layers, if there are many hidden layers, input, and we have hidden layers. If there are many hidden layers, and before output, the gradients in the early layers will become very low as we multiply the derivative of each layer. So the gradient in this layer, it will become low. It will become low, and if it is low, then it will be very slow. If it is slow, it will be very slow, and it will diminish to 0. So that's why last time we learned about one activation function. We can use sigmoid function, and this sigmoid function can give you a higher value. So the gradient from each of this layer will keep stable. The other kind of activation function, we call it ReLU. I think last time we already learned the ReLU, rectifier linear unit. Okay. So the derivative of ReLU function is either 0 or 1. So the derivative is either 0 or 1. Okay. The error signal is also dependent on the width of the network. If the weights of the network are constantly below 0, the gradient will diminish slowly. So if it is always 0, this one, then it will diminish, or it will keep as 0, and the network will not be improved. So in the ReLU, there is another alternative. We can use leaky ReLU. When the gradient is 0, then it will be into the negative. But if it is 1 with the regular ReLU, then we can improve the numbers, so we can keep improving the network. So this is the gate that we learned before. Anyway, this is just the concept about the RNN. I think it is difficult to understand all the things. So at the end of this deep learning, I would like to explain about the performance measures. So the performance of deep learning depends on the parameter setting. What is parameter setting? We learn from the neural network, they are batch size. Or we can also determine the epoch. So it depends on the training size, make the maximum iteration, the maximum iteration training, the maximum iteration of testing. And we also need to understand the optimizer and the loss function. For optimizing the parameter, it tends to use the hyperparameter tuning. So the hyperparameter tuning means we can find what is the best value. There might be some value that degrade the performance, but there might be some value that improve the performance. So this hyperparameter tuning, we will find what is the best value to get a better accuracy, or what is the best value to get a better loss. So I will just give you a very basic optimizer. The optimizer that we usually use in the deep learning, we call it gradient descent. with some other variants such as stochastic gradient descent and mini-beds. And we can also use the adaptive gradient algorithm with variants such as ADA delta, IDEM optimizer. So if you use neural network in the orange, you will see that you can use the ADAM optimizer in the neural network in the orange. Gradient descent. What is the meaning by gradient descent? So it uses a whole training data to update weight and bias. Okay, the keyword is the whole training data. So if you have a lot of data, okay, we will use all the training data to update the weight and the bias. So if we have millions of records, then training becomes slow and computationally very expensive. But if you look at this graph, the loss function will be very smooth. So you will get the best performance at some of time. SGD, or we call it the stochastic gradient descent. SGD, stochastic gradient descent. It solved the gradient descent problem by using only single record. So if I have many records, so I will just use the record number 1, and then I will update the parameters. And then I will go to the next row, I will update the parameters. I will go to the next row and I will update the parameters. But still, SGD is slow to converge because it needs forward and backward propagation for every record. So once we finish with the record 1, we will do the back propagation, and then we will do with the record number 2 forward, and then we will back propagate and then update, and then we will do with the record number 3 and so on. And the path to reach the global minimum becomes very noisy. So if you look at this figure, so when we have the stochastic gradient descent, it will not be very smooth like the gradient descent. It will be very noisy, and sometimes we cannot find out when is the best epoch. Using the mini-beds, this is another variant. The gradient descent overcomes the SDG, the mini-beds GD overcomes the SDG. The SDG is this one. No, this is not SDG, SGD. By using a batch of records. Okay, what does it mean? Batch of records. It is a collection of the records. So if the SGD is only using one single record, the mini-batch GD, it will use several records. So it will use maybe 4 records, 5 records, and so on. Okay. So not only single, but we use several records at once. And it will be used to update the parameter. Since it does not use entire record to update parameter, the path to reach the global minimum is not as smooth as gradient descent. So the result in the gradient descent is smooth, but in the mini-batch GD, it still have some noise, but it is better than the stochastic gradient descent. When we deal with the learning approach, we usually have the loss function. Yes. Loss function, I think you already know, if we use the regression, then we will be able to use mean square error. You still remember what is mean square error? let's say we have the predicted data. The predicted data will be subtracted with the actual data, and then we will do the square. And we will do the summation for all the data, and finally we will divide it with the number of data. So this we call it as the mean square error. If it is binary classification, we can use binary loss or cross entropy loss. And if it is a multi-class classification, we can use categorical cross entropy loss. Binary cross entropy, it is one of the metric, and then it compares each of the predicted probabilities to the actual class output, which can be either 0 or 1. It then calculates the score that penalizes the probabilities based on the distance from the expected value. That means that we can see how close or how far from the actual values. If you're dealing with the multi-class classification problem, you can calculate the log loss in the same way. So let's see with example. Okay, we call it the binary cross entropy if it is a problem of binary classification. Do you still remember what is binary classification? We have only two options, okay? 0 or 1. Yes or no. Okay. So the binary cross entropy is the negative average of the log of corrected predicted probabilities. Okay, what does it mean? Let's say this one. I have predicted probabilities. What is predicted probabilities? The output is given by the model that tells the probability object belongs to the class 1. So let's say that in the binary classification, we have the class 0 and the class 1. So when we have the predicted probabilities, I can say that this is the probability that the result belongs to class 1. So for example, in the ID6, okay, we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, I have 8 data. Okay. Now, for every of these data, I would like to see the predicted probabilities. The actual data is 1. The actual data, like if you look at the data in the iris data set, we have the actual data, the flower name, Setosa versicolor. So this is the data in the actual, we have the label is 1. And then when we run the machine learning, when we learn the deep learning, at the final stage, at the output, we can get the predicted probability is 0.94. We can say that this is close to the 1. So the probability objects belong to class 1 is 0.94. Then it is high. As you know that the probabilities, if it is closer to 1, it is the best one. If it is closer to 0, then it means it is not approaching 1. So if it is closer to 1, then we can measure the distance. We call this is the predicted probabilities of the class 1, the probability belong to the class 1. So we don't need to correct it because this is already the probability belongs to the class 1. So the corrected probabilities, this is a new column. The corrected probabilities will be the same values because the corrected probabilities here, it should be the probability object belong to class 1. Now let's see the ID one, the actual is 1 and the predicted probability is 0.9. Okay, the corrected probabilities is also 0.9. ID 7, the actual is 1. The predicted probabilities is 0.78. Okay, the corrected probabilities is also the same. ID 8, the actual is 0. Okay. What is the predicted probabilities? It is the probability the object belongs to class 1. But the actual is 0. So in order to check the corrected probabilities, we need to subtract. The corrected probabilities will be 1 minus 0.56 because the maximum of probabilities is 1. So the value 0.44 will be here. Let's see another example. ID 2. The actual is 0. The probability or the predicted probability is the probability object belongs to class 1. However, we know the actual is 0. So the corrected probabilities will be 1 minus 0.51. So the result is 0.49. So we correct the probabilities into 0.49. Okay. ID 3. Okay, this is the same because the actual is 1. ID 4, the actual is 1. And ID 5, okay, the actual is 0. Then we need to correct the probabilities. So the corrected probabilities now becomes 0.9. Okay. After we have all the corrected probabilities, we will do the log. What is log? Log values over less penalty for small differences between predicted probabilities and the corrected probabilities. So the corrected probabilities 0.94 means it is nearby 1. Okay, then the difference will be very small to 1. This is also nearby 1. The distance will be very small. But if you look at this number 0.32, it is very far from 1. That's why the result will be very high for 1. So when the difference is large, then the penalty will be higher. Okay. So we need to do with log. Maybe I can show you. Log. We have 0.94. And then I use log here. So the result is minus 0.026872. So you can see here, log of 0.94 is 0.026872 and so on. So let me check again. Still, yeah. Let me check again. 0.9, the corrected probabilities. 0.9, and then I will do log, then I can get 0.04575 negative. So this is the result, 0.04575 negative. And then we have other numbers. So you can look at, you can use the calculator. That's why you need to bring your calculator during the final exam, because there will be the similar calculation like this. So for example, 0.78, you can log, then the result is minus 0.107905 and so on. Okay. Now we have the binary cross entropy formula like this one. We will do the log, and then we will do the summation, and we will divide with the n and then multiply with minus. So every minus here will be positive. Okay. So the value of the negative average of corrected probabilities we calculate comes to be 0.214, which is our log loss or binary cross entropy for this particular example. So how can we get this 0.214? We need to do the summation. So all numbers are negative. Okay. All numbers are negative. So let me just skip the negative, because at the end you will multiply with negative. So negative multiply with negative, it will be positive. So let me just use the positive, this number. Let's say I have 0.0268 plus 0.04575 plus 0.1079 plus 0.3565 plus 0.3098 plus 0.3279 plus 0.4948 plus 0.04575. Then, okay, we can get the value 1.7152. So I just remove the negative value. After I have the summation, I will divide with n. What's n? N is the number of the data. 1, 2, 3, 4, 5, 6, 7, 8. Then I will divide with 8. Then the result is 0.2144. So I will just make 0.214, and this is the binary cross entropy loss, or this is the log loss. So the log loss can be also using this formula. We can also use this formula, log loss. So it means the yi multiplied by log the probability, the corrected probabilities, plus 1 minus yi multiplied by log 1 minus probability. So basically, you can use also this one for the log loss, or you can use the binary cross entropy to measure the loss. So here we use the binary cross entropy to get the loss, which is the 0.214. If we deal with the multi-class classification, you can use different approach. We have the two summation of the yij multiplied by log pij. So n represent the number of rows and m represent the number of classes. Okay, so please review this one, because there will be one problem about this in the final exam. Okay. Okay, so this is the end of this class. So I'm just giving you some trend at this data mining. Maybe you will not find any word of data mining these days, but people try to give a broader words like data science, or they use the data analytics, or they use the machine learning. And there are many data mining or data science issue in the healthcare industries, like in the COVID-19. Yeah, it is very big job for the data scientists. Automation in data mining. So when you use Orange, so it is kind of flow, and you can automate. If you already have the flow, then you can reuse the flow for every of data set, which is similar. And there can be some embedded data mining. For example, this is from the Samsung SDS. They have the Brightix AI. So for the process here, this is a process in the company, and they will have some activities, and in the every activities they can embed the data mining. And nowadays, you know, the automated vehicles. So the automated vehicles means, yeah, the vehicles without any drivers. So the spatial and the geographical data mining becomes important. We want to know which location that is dangerous, which location which have the high density, which location which have high traffic, and so on. So it is rising. And also we need to understand not only Orange. You only learn only one tool, Orange. But actually there are many other tools that you can use for this data mining project. You can use the RapidMiner, which is based on Java. Nime, which is based on Java. Or yeah, Weka is also based on Java. Python, and so on. And you can also use some commercial tool like the Oracle Business Intelligence and SAS data mining. Okay, that's all that we can learn from one semester. So if you want to look at the Python code, I give you the source code. So you can look at this source code. If you have interest to learn more about the deep learning, you can look at this code. This is about the regression, and this is about the classification. Okay, so in the regression here, I used the LSTM. So you can look how we can use the LSTM in the Python. We use the loss mean square error, and the optimizer is Adam, and the other is the using CNN. So we have the convolution 2D, max pooling, okay, the activation is ReLU. So you already learned all those things. Yeah, you can look at the code if you have interest. Yeah, you can try to deal with this code. Okay, that's all that I can explain during one semester.